So this is a bit of a tricky question. So let's go over the first one first, and let's go back and take a look at the code. So most of these are arithmetic operations, and if you remember from the RAM model that we've been discussing in the lecture, that according to the RAM model we've been using, all arithmetic operations take constant time. So that means this, 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 and this all take constant time. The only thing that doesn't is this for loop right here. So how many times does the for loop execute? Well, it executes based on n, the value of the input, about square root of n times. And if everything else is constant time, and this executes square root of n times, well, then we're on the order of the square root of n. So we can go ahead and check this. So this next part is really pretty tricky, and it hinges on getting this first part right. So if you had trouble with this, that is totally understandable. So first, let's remember that we can represent n with a logarithmic number of digits, which is what d is. What this means is that n equals c, where c is just some constant that we're multiplying by, times 10 to the d minus 1. And as an example of this, let's say that n is 4,000 like we had before. So 4,000 equals c, where c is something, times 10 to the 1, 2, 3, 4. d is 4 minus 1 is 3. And well, then that means that this has to be 4. 4 times 10 cubed is 4,000. So this is how we're representing n by d. And c is just some constant to make everything work out. And since this is big O notation, we're not really that concerned with constants. Now, if we know this, and we also know that the algorithm has a running time of on the order of square root of n, when we're talking about it in terms of n, well, then we can put these together. So square root of n is the square root of all of this. And we're going to have to do a bit of math here. Well, we can separate these two out to be square root of c times the square root of 10 to the d minus 1. Well, we can describe this by saying it's 10 to the d minus 1 over 2, since that's exactly what the square root is. But now we can pull this out. And so now we have these nice 3 separate terms. And again, since we don't really care about constants, we can just kind of get rid of these. We can say that square root of c times 10 to the negative 1/2 is just some other constant we don't really care about called k, since the only thing we really care about is d. So this is k times 10 to the d over 2. And this is exactly what we need to say what this algorithm is in big O notation. And so we can say that in terms of d, the running time of this algorithm is big O of 10 to the d over 2. Now, if you didn't get that or if you had problems with it, don't worry about that. That's really kind of a challenging problem. And if you still don't understand it, then I'd recommend checking out the forums and discussing it, because this is really the kind of basic math calculations that you're going to have to do. And part of the problem here that a lot of people run into is these constants that we just drop or don't care about, really. And that's the kind of thing that makes big O notation really very powerful, that we can just drop those and say, we don't really care about those in the grand scheme of things.